Okay, so welcome back to another video. So here we have an integral from 1 to 2 of e to the x times x minus 1 divided by x times x plus e to the power x dx. So that's a lot of x's we have over there. So too many, nothing wrong with that, but actually the result is actually pretty nice in that aspect. So we don't even need to do any sort of generalization or find something to, make the integral a little bit simpler. Instead, I say simpler in the sense that we don't have to get so tedious, but this is actually a simple thing that we actually need to, get our hands a little dirty just a bit. But afterwards, once you have that, we actually follows a nice little u substitution. And simply using that, it actually just makes a whole lot of things like disappear and make things, finding its antiderivative a whole lot simpler from there. So not too much going on today. This video is actually going to be a very short one, but I feel like this integral is actually I think an interesting one that is worth showing to you guys. So another creative approach to, to utilize, in your learning to that aspect. So with that, why don't we actually jump right in? So I'll call our integral capital I, and then what I'm going to do is for both our numerator and denominator, I'm actually going to multiply a 1 divided by x squared. So I have e to the power x and then x minus 1 multiplied by 1 divided by x squared. Under our denominator is going to be x, then multiplied by x plus e to the power x, also multiplied by 1 divided by x squared, followed with dx. So if I actually simplify some things out and well, not just yet. So let's actually move the x squared back into over here. So we have the integral from 1 to 2. So e to the x, and then what I'll have is going to be x minus 1 and then divided by x squared on the bottom. Then I have on the bottom, so I have x and then multiplied by e to the power x. Or first I'll write this as x plus e to the power x. It doesn't really matter. It's just the way I wrote it. It's addition. It's commutative, so it's okay. Plus x. Or plus e to the power x, and then divided by x squared, followed by dx. So we can simplify further such that there's some things that can cancel from over here. So we actually reduce this to a subtraction of rational functions. So I have 1 to 2 of e to the power x multiplied by, so what is it, 1 divided by x, and then subtract 1 divided by x squared. So under our denominator, I have, this is actually going to be, so the x is just going to cancel, and then I can actually reduce this to say that I have e to the power x plus x, and then divided by x, then dx. Then we can reduce this even further such that, specifically looking at our denominator, so I have from 1 to 2 of e to the x, and then 1 divided by x minus 1 divided by x squared. Under our denominator is going to be e to the power x divided by x, and then add this with 1 and dx. All right. So that's as far as we can go, but now let's actually now perform our nice little u-sub that we're actually going to perform. So you might be thinking, what u-sub are we actually going to use such that this is actually going to make things, it's going to clear everything up. So let's actually utilize our denominator over here. We're going to let u equals e to the power x divided by x plus 1. Then our differentiation du, then we just apply the quotient rule. The derivative of 1 is simply just going to be 0. So if I apply quotient rule for e to the x divided by x, what we have is x times e to the x, then minus e to the x, and then divided by x squared dx. Then we can actually simplify this further such that this is going to be e to the x if I factor this out. So I have x and then subtract 1 and then divided by x squared dx. And then again, if I want to simplify even further, that the x squared is going to associate with our quantity of x minus 1 and just divide those x's, I have e to the x and then multiplied by 1 divided by x minus 1 divided by x squared dx. And perfectly enough, look what's in our denominator and what cancels? Boom. So we just substitute our du differential for our over here. So now what this reduces to is that I is going to equal to, let me just move that up a little more. What we have that I is going to equal to our new integral. So that means that I have to plug in our bounds. So for 2, this is going to be, what is it? So 1/2 e to the power 2 plus 1. I plug in 1, so I have e to the 1, so e and then plus 1. So we write that 1/2 e squared plus 1, and then e plus 1. And so that cancels with the du, and then that's just become u. So I have a 1 divided by u du. Obviously, we know that the well-known antiderivative of 1 over u is going to be just the natural log of u. Evaluate this at our bound from 1/2 e squared plus 1, and then e plus 1, and then applying the natural law property since it's under subtraction. So now what we have is that this is going to be ln of 1/2 e squared plus 1, and then divide it by e plus 1. And for our final step, let's simplify this even further so we don't have a rational number on our numerator. We'll multiply 2 just to get rid of that 2 from the denominator. We have that our final answer is just going to be equal to e squared and then plus 2, all this being divided by 2e plus 2. And so with that, our final answer is this nice natural log consisting of, the e base, and we have 2's over here. And again, no generalization needed. We just took something of a little creative approach that kind of looks heinous from a first glance, but reduces everything nice that we actually use. We utilize a u-sub that actually makes things a little simpler from getting into our 1 over u, finding its well-known antiderivative, putting in the bounds, and then simply just reducing. So yeah, that's pretty cool if you ask me.